So with this problem, we are looking at a confidence interval with a margin of error of 3%. So the point estimate is 38%. That's our p hat. So that means that we've got on either side of that. So remember, we can kind of think of it like this, where you have your point estimate in the middle. That's 0.38. Margin of error of 3% means we're going to go out as far as 41% and 35%. And we would expect the true proportion of drivers who are willing to pay higher gas prices to protect the environment. We expect that to fall between 0.35 and 0.41. We're not saying where it is exactly, but we feel some percent confident it's going to be in there. So as we go through and read these, 3% of those surveyed refused to participate in the poll. That's A. That is not what a 3% margin of error means. B says it would not be unexpected for 3% of the population to readily agree to the higher gas prices. Well, we've already established it's going to be in this range from 0.35 to 0.41. Between 343 and 402 of the 980 drivers surveyed responded that they'd be willing to pay higher gas prices to protect the environment. Well, we got an exact number when we did the survey. We're not estimating how many in the survey, we're estimating how many in the population. So it's not that. If a similar survey of 980 American drivers was taken weekly, a 3% change in each week's results would not be unexpected. Now that's somewhat tempting, but that's really not what a margin of error means. It means that last one. It is likely that between 35 and 41% of the driving population would be willing to pay higher gas prices to protect the environment. There's your answer. So, I mean, that is a somewhat tempting explanation for D, but that is not really what a margin of error means. Okay, there we are. Okay, now this is what we're doing today. I kept saying, and I'm probably gonna keep saying that what we did the first semester is kind of gathering the ingredients. Now we're making some recipes, and you'll hopefully see that very clearly today, that we already learned a lot of stuff about sampling distributions, about the normal distribution and calculations. And you can see all the changes that we're making today to do our, what sounds intimidating here, the one sample z-test for proportions. This one sample z-test for proportions is really just combining a couple of concepts together and doing calculations that you're already familiar with. There's just a few things to keep in mind as you do it, but really, I hope as we keep going through, you're like, oh, it's just one slight change, no big deal. So that's why I'm really hoping you find the second semester a lot easier. Now, before we jump into that, we do need to kind of review just a little bit on sampling distributions. And this was the last thing we did right before break. We didn't maybe spend a sufficient amount of time with it, but we do have some, if I can think clearly, but we can kind of cover the important concepts. So you might have a distribution of in the population, but of course a sampling distribution, it's a little weird to talk about proportions with a sampling distribution. So a sampling distribution for proportions is if you took a sample of size anything, let's say this is a sample of 100 people. We have the mean of our sampling distribution for proportions p hat would be equivalent to the true population proportion. And the standard error here, as we call it, is the, well, really it's the standard deviation. Standard error is something a little different. The standard deviation of our sampling distribution, in this case, is going to be that true proportion times 1 minus p, all divided by n, and then the square root of that. So that creates our standard deviation right here. And now we can kind of tie this into what we're about to do. So we are going to be looking at a sample of that was taken from some population, and we're going to be looking at the proportion that we got as a result. And we want to figure out, is this an unusual result to get? And is this evidence that maybe our proportion given isn't correct? So we're testing that proportion right there to see if it's even plausible at a certain significance level. So let's say that we got a sample, and whatever the result was, our result was right here, our p hat. Now, is this p hat something that we would expect to get just by random chance? It is possible, of course. You can see there's still area under the curve. This could possibly happen by random chance, but is it something we'd expect to get by random chance? And so we set up a confidence level, not a confidence level, a significance level, alpha of maybe 0.05 that says, you know, if this particular p hat has less than a 5% chance of happening, we're going to say that maybe this proportion isn't correct. And what we have is, this is not, when I say p right here, this is not the true population proportion. This is the presumed one. We call it p sub naught because it's going to be our assumed one from the null hypothesis. And we're going to see this very clearly. But really, just to go over it real quick, we are going to be setting up a normal curve based on certain parameters. And then we're going to compare our p hat to our normal curve and see if it's an unlikely result. If it's unlikely, then we're going to say that, you know what, this p sub naught is not likely to be true. We have evidence that it's not true and we're going to reject it. Okay, so hopefully just you're able to follow conceptually what's going on. We're going to go through the full steps of this. But here we're going to kind of talk about the one sample z-test for proportions. So when we were looking at normal distributions, this should be very familiar to you. We have the value minus the mean divided by the standard deviation to give us a z-score. You're comfortable with that. You should be by now. Now we adapt this just slightly to make it look like this. The test statistic is still a z. It's not technically a z-score, but it's kind of a z-score. Maybe it is a z-score, but whatever the case, it's our statistic minus a parameter divided by the standard error of the statistic, and this can be found on the AP formula sheet. So let me share the formula sheet real quick. So we were already looking at this, the generic confidence interval formula, and you will need to be able to refer back to that and know how to plug stuff in. The standardized test statistic is going to be right here, and we're going to have 4 different, if I remember correctly, 4 different times that we use this test statistic. And we will need to plug in a different statistic, parameter, standard error of the statistic, 4 different types of problems that will be using this. Actually 5. And maybe I'm forgetting something. There's also the confidence interval. There's 4 different ways that we might use a confidence interval by plugging different values in here. Critical value, standard error, all that fun stuff. All right. So that can be found here, and the actual standard error will depend on the type of problem we're looking at. So you can see all the different standard errors right here. And there we go. Let me switch back to the presentation. Okay, so looking at this now, this is of course the z-score that you're very familiar with, and this is plugging stuff in. Here's what we've got. Our z-score here is going to be p hat minus p sub naught divided by, and you can see we're using p sub naught divided by n and all that jazz. Okay. So this is not a formula given. This is one where you would have to plug it in. This would be, if I go back one slide, notice the statistic, parameter, and standard error. I'm just going to replace statistic, parameter, and standard error with what it is for this particular case. Statistic, parameter, standard error. Right, so I can replace these with all kinds of different things depending on the scenario. Okay, moving on. So it helps us conduct the one sample z-test for proportions. That for proportions part is kind of redundant. We only use z-test for proportions, but you know, it's not a bad thing to have it there. So it's a z-score for the sampling distribution for proportions with the same sample size as p hat was generated from. So we're going to create a normal curve using the given null hypothesis. Well, but I'm kind of jumping a bit ahead. So let's kind of work through this a little more. Once we have a normal curve and we have what the z-score on that curve is going to be. We can find the p-value. It's just the area under the curve, but we call it specifically a p-value. And just to repeat what I said before, if that value is small enough, then we consider it statistically significant, and we can reject the mean, or we can reject the null hypothesis. And there it is. So we'll run through this full process. Because we're assuming the null hypothesis is true, we are using the null proportion right here to calculate the standard error of the statistic. This is not p hat. We were using p hat when we were doing confidence intervals because in that situation, we had no idea what the true population proportion was. So all we could use is p hat, and we were getting a standard error. Now, technically, this might be considered a standard deviation because what we're saying is the null hypothesis proportion that we're going to use, we're going to plug that in right here. And we are assuming that that is the population proportion. Okay, so we don't use p hat in this part of the calculation. Keep that in mind. That's a very common error. All right. Now, this is technically a standard deviation, but in a generic formula, AP calls this a standard error. It's just a minor technical piece of information. I don't think that distinction is going to matter. If it does, I'll get back to you, but I currently don't think it's going to matter. Okay, let's pause and consider what we're doing. We're finding a z-score and calculating the area under the curve. We've made that pretty clear. So if we're going to do this, we have to make sure these calculations are appropriate, and we need to check certain conditions. And hopefully by now, you're familiar with what those conditions are. We need to check. Is it random? This is to make sure it's an unbiased estimator. Is it less than 10% of the population? And this will make sure that our calculations are going to be accurate enough. Now, an alternative is that if it's independent trials, then that also meets the 10% condition. The 10% is for not independent whenever it's without replacement, all that kind of fun stuff. But anyways, and then is it normal? This is to make sure that using normal CDF calculations are appropriate. And we're going to use large counts for proportions. So of these three, and I've said this before, this one is essential. There is no getting around this. It has to be a random sample, or else none of this is worth anything. These two, you can fudge it a little bit. If we don't meet these conditions, then we can kind of make a comment to that effect. Like, we didn't quite meet this condition, but, you know, take these results with a grain of salt. And it is theoretically possible that you don't meet one of the two. All right. Is there anything else to say? Yes, here we go. Here's kind of the process we're going to go through. Write your hypotheses, the null and the alternative hypothesis, and we need to figure out a significance level. If you don't know which significant level to use, it doesn't tell you, just use a 0.05. It's always a safe one. It might tell you to use the 0.01 significance level. All right, then we need to check our conditions for inference, the ones we just went through, random, 10%, and normal. Calculate the test statistic, and that's going to be using that right there. Find the p-value by running a normal CDF calculation with that test statistic, and then we're going to interpret the results. Okay, that's it. Right here, draw a picture as you go through. So draw that normal curve, show where things would fall on the sampling distribution, and you know, we'll see that as we work through. So let's do some practice. Okay, a new player joins the Flag High basketball team. She claims to be an 85% free throw shooter. Thinking that she's exaggerating her skill, you observe her during practice and see that she makes 38 of 48 free throws. Is her claim true? Okay, so the first thing we want to do is establish our hypotheses, H sub naught and H sub A. The null hypothesis is always that the the claimed proportion is true, if that makes sense. So she claims to be an 85% free throw shooter. So this will be, I'm writing P sub naught, but that's going to be our hypothesis that this is true, that the true proportion is 0.85. Now, the alternative, we're skeptical that and we think she's exaggerating. So we think she's actually not an 85% free throw shooter. We think her true proportion is less than 85%. Okay. So that's all good. Let's determine a significance level. It doesn't tell us which one to use, so I'm just going to use a 0.05 significance level. Now, I've got right here 38 of 48 free throws were made, which gives me a p hat when I do the division right there. P hat is going to be 0.7917. It's just 38 divided by 48. Now, P sub naught, because this is the assumed proportion, we're not saying this is the actual population proportion, we're saying it's the assumed one. So that value is our P sub naught. We want to use that for the most part when we get to our calculations. All right, so we're ready to move forward. We want to go ahead and do where do I want to do this? Right here. A one sample z-test. So you might call this kind of the state part of your problem. This is the plan part. And we want to check our conditions. Is it random? Well, what we've got going on here is that these are all independent trials. So yes, it would be considered random, or sorry, it is random because we're going to assume that these are just any free throws apply here. So it's always random here. I was jumping ahead. The 10% is something we can kind of ignore because these are independent. We're assuming that whether she makes one free throw from the next doesn't depend on how she's done before. And the last one is it normal? And the way we check this is with large counts. So n times p and n times 1 minus p. And I'm going to use p sub naught for this. So I got 48 times 0.85. And I've got 48 times 0.15. And you're going to see we run into some problems here. So 48 times 0.85, we're good with that. That's 40.8. But 48 times 0.15 only gives us 7.2. So did we meet this condition? Technically, no. But we're not going to stop here. We are going to continue with the calculations. And I would just want to add some kind of a comment here that says, we didn't meet the normal condition. So our results might be inaccurate. Okay. So, I mean, we can just make that claim. It shows that we know what we're doing. We know that we didn't meet these conditions and that we're not going to necessarily get the most accurate results here, but we can move forward and just kind of have that asterisk next to this. So now we want to move on to the do part of this, which is going to be our test statistic. So the stat minus the parameter. And I should add, I hope it's obvious enough, as I'm going through this, hopefully you guys are following along, whether you're copying down what I'm doing or just kind of making some notes for yourself that will help you remember this. This is recorded so you can watch it later. So the stat and the parameter, that's our generic formula. So now I want to kind of plug stuff in. I'm going to use p hat minus p sub naught divided by the square root of p sub naught times 1 minus p sub naught divided by n. And now I can plug stuff in. This just It might seem unnecessary to you, but this gives a very, very clear indication. No one's going to be confused on if you know what you're doing. So p hat is 0.7917 minus p sub naught is 0.85. That's an assumed proportion. And then I'll just plug in from there. So it's going to be 0.85 times 0.15 divided by n is 48 free throws. Now, one thing it might be kind of worth doing is calculating the standard error separately. So I'm going to do that first. You don't have to, but I'll show you why I'm doing it. 0.85 times 0.15 divided by 48. My standard error here is 0.0515. And of course, 0.7917 minus 0.85 is negative 0.0583. And I got, for my test statistic, 1.13. And that'll be good enough. You could go one decimal further, 1.131. All right, it is important to be able to, not that you're going to be talking with other people when you take this AP test, but it is going to be important that you understand that this is not a z-score right here. It is kind of, but it's your test statistic. So if they're asking for your test statistic, it's your z-score. Okay, now before I finish this off and do the final calculation, I want to draw a diagram. So I want to have a normal curve. We already decided it's not normal. So this is going to be a quiz for you, for your conceptual understanding. If this is not meeting the normal condition, how will this be different from a true normal curve? And I can give a hint unless someone has an answer they're about to say. Okay, your hint is it's not going to be normal completely. It's going to be skewed. So will this be skewed to the left or skewed to the right?
Skewed to the left.
Very good. It would be skewed to the left. And of course, the reason for that, we're looking at proportions. Proportions can only be between 0 and 1. So if we're at 0.85 way up here, the only way for this to be skewed is off to the left. All right. So we didn't, now if we have enough samples, then it's going to look more like this. So it's going to be approximately normal anyway. But because we don't quite have enough, it's going to be slightly skewed to the left. And we're just going to work with that. Okay. So good job, Amanda. And all those of you who didn't answer but had that answer in your head. Okay, so I wanted to look at this real quick. My standard error is 0.0515. That's going to tell me how far I'm moving up. So I'm just going to round it to 0.05 to make it easier. This is about 90% right here. And one more out is going to be 0.95. To the left, this is going to be about 0.80. And it's going to be about 0.75. There we go. So our normal curve looks approximately like this. And that 0.7917 would fall somewhere about where I just marked it. And this would be my test statistic right here, the negative 1.131 standard errors away from the mean. So I want to find out what is the area under the curve this way. And now I can do that. I'm going to do a normal CDF calculation. Again, we can't technically do the normal CDF since we didn't meet that condition, but it's going to be close enough, and we're going to see what's going on here. Keep in mind, I want to go from negative infinity up to the negative 1.131 with our standardized normal model. This was asked in 5th hour, how do we do normal CDF, just because people had forgotten. Remember, go to second, and then variables distribution menu is up above that, and you can find it from there. And I got as an answer 0.129. So here's the deal with this one. This 0.129 is not 100% accurate, but it is not so inaccurate that we can't draw a conclusion from this. All right, if we added more free throws, I don't think it would change our calculations by enough to make this statistically significant. So we're going to summarize now. I'll try and squeeze this in. Because the p-value, and that's what we calculated here, this is a p-value. Because the p-value 0.129 was greater than the alpha level, which was 0.05, we fail to reject the null hypothesis.
Yeah, how funny it would be.
Okay, so this was not unusual enough for us to decide that this 85% isn't true. And of course, what I'm saying is that if she really is an 85% free throw shooter, we might expect her to only make 38 out of 48 about 13% of the time, plus or minus a little because of our uncertainty. So about 13% of the time, this could happen. That's not super unusual, because she could equally get 88% of the free throws the next time she shoots 48 of them, right? So these are just kind of fluctuations that can happen. So if it was a really low p-value, we would say, okay, that's very, very unusual. If she's really an 85% free throw shooter, she should not have been this bad. So maybe she's really not an 85% free throw shooter. Okay, now the last little bit, I'm not going to try and squeeze it in the corner. I'm just going to write it at the top. I will just say this. We do not have convincing evidence that she is not an 85% free throw shooter. Okay. Of course, that would all be together. I just didn't quite have the room. Okay, before I move on, are there any questions here about where any of these numbers came from or any part of the process? Okay. I just added the C down here at the bottom. That's kind of the conclude part of our 4-step problem.
Why did we use 0.05 as our significance level?
That's a good question. It doesn't tell us which significance level to use. So if that's the case, 0.05 is always one you can just kind of fall back to.
What about 0.01? Didn't we talk about that yesterday too?
0.01 is commonly used. And here's the thing where maybe I need to do a little bit more research on this. And I don't know if it was mentioned in the chapter. 0.05 and 0.01 are both very common. If you're not told, I say it's always pretty safe just use the 0.05 level. I think if it was an FRQ, they would tell you what significance level to use. there are maybe some general rules you want to follow. Like sometimes if it's for medical purposes, then you kind of want to be more stringent, use the 0.01 level. I know that, but I think without any other information in the problem, I would just say by default, go back to a 0.05. I don't know if that's a satisfying answer, but hopefully in problems it gives you a significance level. You'll notice that in all the problems today, it doesn't give us one to use. Okay, so if there's still questions, you can ask those and we'll talk about it more. Okay, so let's look at this one. We've now got, you can see this from the textbook. In the 80s, it was generally believed that congenital abnormalities affected about 5% of the nation's children. Some people believe that the increase in the number of chemicals in the environment has led to an increase in the incidence of abnormalities. A recent study examined 384 children and found that 46 of them showed signs of an abnormality. Is this strong evidence that the risk has increased? Okay, so we want to write our appropriate hypotheses. That's going to be the very first part. We might call this the state part of our problem. So my null hypothesis is that we have not changed from that 5%. I'll go ahead and label this as P sub naught up here. So my hypothesis is that the true proportion is still 0.05. The alternative hypothesis is that, well, we're concerned that this percentage has increased, and it actually tells us increased right there. So I think that our true proportion is now greater than 0.05. And I'll go ahead and say for significance level, we can still use a 0.05 here. This might be a situation where you say, well, this is dealing with like health outcomes. And maybe we want to use a 0.01 to be way more certain about this. And we'll learn about the problems that come up if you, basically if you pick the wrong significance level and you make a mistake. We'll learn about that tomorrow. But for now, let's just say that this 0.05 is our significance level and move forward. All right, so we're good with that. Now let's check our conditions. First of all, we're going to do a 1 sample z-test for proportions. And now, is it random? So this is the kind of stuff where it doesn't specifically say that this study was randomly generated, but I think it's fair that if it's a study, they included randomization in the process. So I would maybe write a sentence to that effect, but I'm going to say, yes, it is random. 10%. These are not independent because we're sampling without replacement, but 384 children is definitely less than the number of children. So it definitely meets the 10%. And is it normal? Well, let's see. Okay, we can already tell that it's going to be normal because 46 were successes, if you will, which means the others were failures in, this sort of binomial setting. So I already know that both of them are greater than 10, but we can kind of do this more formally. We need to calculate p hat anyway, which is 46 divided by 384, which is 0.12 when you round that off. If you want to get, 0.12. If you want to get more specific than that, that's fine, but this is going to be plenty good for our purposes because it'll be 0.120. Okay. So p hat is 0.120. If I multiply that back out, I'm going to get n times p is equal to 46. And n times 1 minus p will be the leftovers. So 384 minus 46 is 338. Yes, we've met the normal condition. Very good. This was the plan part of it. I'll just put a P right here. So now we're going to calculate. Our test statistic is the stat minus the parameter divided by the standard error. Specifically in this case, it's going to be p hat minus p sub naught divided by the square root of p sub naught times 1 minus p sub naught divided by 9, or n, not 9. And I'll just substitute some values in. That is going to be, my p hat is 0.120 minus 0.05 divided by, that's going to be, it's p sub naught, so it's going to be 0.05. Make sure you're using the correct proportion. This is where most people will make mistakes. All right, 0.05, you got to use p sub naught here because that is a presumed population proportion. Divided by n is 384. And I want to test your statistical intuition right now. Without even calculating this, do you think this is going to be a statistically significant result?
Yes.
Yes. And now hopefully you're getting to the point where you can tell if something is a big difference statistically speaking. All right. And being familiar with z-score calculations at this point, hopefully you can look at this and realize that is a heck of a big difference, going from 5% to 12%. So we'll do the calculations, but hopefully that bell's already going off saying like, wow, this is going to be a really big difference. Okay, so it's going to be 0.07 on the top, but I want to calculate the standard error. Which is 0.011. I'll just add one more on there. And I can do the division, of course. And that is crazy. 6.29. I almost feel like we don't even need to bother with that normal CDF calculation. We will, but I mean, this is a huge z-score. All right, so let's kind of draw what's going on. We got a normal curve. We did meet our normal condition. I'm going to draw this long tail coming out. This tail would continue off to the left as well, but we don't care about that way. The p sub naught right here is at 0.05. I'm going to round this off. Our standard error is about 0.01. So I know it's not exact right here, but it doesn't matter a great deal. So this goes to 0.06, 0.07, 0.08, 0.09, 0.10, 0.11, 0.12. Look at that. We're looking for something way out here. And we want to see the odds of getting this part of the curve. Look at how far out that is. And I really, really want that to sink in, just how big of a z-score that is. All right, but we can move forward from here. This is going to be a normal CDF calculation. No caveats required on this one. We're going to go from 6.29 up to positive infinity with a 0, 1, the standardized normal model. And we get this incredibly small number. This is going to be 1.59 times 10 to the negative 10th. Okay. So I think we're ready to interpret this. I will say, having this diagram, first of all, it's going to make just the process make a lot more sense for you when you draw this diagram. But secondly, this is going to really show visually to the graders that you know what you're doing. I repeat myself a lot. You've heard me say stuff like that, but I can't emphasize enough how important it is to draw this diagram. Okay, so now let's kind of write our conclusion. Because the p-value, which is 1.59 times 10 to the negative 10th, is less than the significance level, which is 0.05, we will reject the null hypothesis. Again, the null hypothesis is that it's still 5%. Nothing's changed. Well, we can easily reject that one. So we have convincing evidence that the rate of abnormalities has increased. All right. So this is kind of our conclusion right here. I'll circle that. Okay, and pausing there for any questions. All righty then. We will look at one last concept in this chapter. I'm gonna have to stop sharing for a second, and I'll share again. All right, this is also in the chapter, so those of you who read, this will just be a little review for you. We have one-tailed and two-tailed tests. So with both of the previous examples, we had good reason to believe that the alternative hypothesis should be either greater than or less than the null hypothesis. In the first one with the free throw shooting, we thought that the true value should be less than the null hypothesis. In the second one, we thought that the true value should be greater than the null hypothesis. Now, in those cases, we were conducting what we call a one-tailed test, and we were calculating the area only under one of the tails. But we could run into a problem where we aren't sure if the alternative hypothesis should be one way or the other. So we just say the alternative will not equal the null. We're not saying it's going to be greater than or less than, it's just not going to equal it. So that's what it would look like. Now I should change that actually to, if I can write, I should change that to P sub naught, not H sub naught. But anyways, this is a two-tailed test because we're testing both directions of change. You want to test two of the tails. All right. So luckily, I mean, it seems like we have to add another layer of complication, but the only difference is once we determine it's a two-tailed test, we are going to double our p-value, and that's it. And then we can still compare it to our significance level. So if the doubled p-value is below the significance level, we can determine that there's a statistically significant difference that can't be explained by random chance, and we can reject the null hypothesis. Wait, is there something else here? No. So when we're determining which one we should use, should we do like a p is greater than, p is less than, which would be one-tailed, or should we do p is not equal to? How do we determine that? Well, that's going to be found in the question prompt. So if the question explicitly states that the difference is in one direction, or it's expected to be in one direction, we're going to use that one-tailed test. But if it simply says that the value is different or not the same, or that the null value is not accurate, then we will conduct a two-tailed test to cover all bases. So if you're not sure the two-tailed test is more conservative, it's always better to go with that. So we have a couple of general rules now. It says, if we're not sure what significance level to use, then use 0.05. If we're not sure to use a one or two-tailed test, use the two-tailed. So this is going to give us honestly, it's not the most conservative, but it's just kind of the most generic. In the two-tailed case, it's the most conservative calculation we can do, but this is just kind of the most generic significance level to deal with. Okay, now everything is conducted exactly the same way. Just at the end, we double the p-value. So it's not mathematically and conceptually that challenging. You just have to keep it in mind. All right, so now let's look at this one. The National Center for Education Statistics monitors many aspects of elementary and secondary education nationwide. Their 1996 numbers are often used as a baseline to assess changes. In 1996, 31% of students reported that their mothers had graduated from college. In 2000, responses from 8,368 students found that this figure had grown to 32%. Is this evidence of a change in education level among mothers? Our hypothesis. Now, it's not asking if it is an increase or a decrease. It's just saying, is there a change going on? So as you might imagine, we're going to look at a case where our null hypothesis is that the true proportion hasn't changed. It was 31% in 1996. It's still 31%. The alternative hypothesis says that proportion is not 31%. I don't know if it's increasing or decreasing, but it's not the same anymore. And just so we can have this, the p sub naught in this case is going to be 0.31. The n number in the sample size is going to be 8,368. Our significance level, we can use 0.05. P hat is going to be 0.32. So now I'm going to test your statistical intuition again. Do you guys think this is going to be statistically significant? And I know this feels like a trick question.
No, because
Okay.
the proportion only went up 1%.
And that's fair. So now to further dig into this, and it can be anyone to answer, why might it still be statistically significant? What kind of clues you in that maybe this is statistically significant?
The sample size, maybe?
Perfect. That's exactly right. This is a huge sample size. So you have to remember that as your sample size gets bigger, your standard error gets way, way, way small. So we're going to see a standard error in a little bit that's really, really small. So that 1% difference might be statistically significant. All right. So this is kind of the state part of the problem. We're about to do the one sample z-test for proportions. And I should add in right here that some of you are already aware that your calculator can do these tests for you just by plugging in a few parameters. And I'm intentionally not showing you guys how to do that, all right? Because I want you to show your full work and be in the habit of doing that. So yes, your calculator can do this work for you, but we're not going to be lazy. All right. So the plan, we need to check, is it random? Doesn't explicitly say it, we're going to assume that it is. Is it 10%? As big as that sample size is, we're talking about students, and there are millions of students. So yeah, that's way less than 10%. And is it normal? Now, I'm not even going to waste my time calculating this. Now, I would on an AP test, but with a sample size that big, there's pretty much no proportion you could throw out that's going to make that not normal. That is such a huge, so remember, it's n times p and n times 1 minus p. That sample size is so big, yes, we've met it. Okay, we kind of did that a bit in a lazy way, but you'll know what to do. Okay, now we're going to do some work. We're going to write out our test statistic again, the stat minus the parameter divided by the standard error. And in this case, that is p hat minus p sub naught divided by p sub naught times 1 minus p sub naught divided by n and the square root of all that. Plug some numbers in. This is going to be 0.32 as p hat. And notice, remember, this is where I kept all the numbers I'm going to plug in. Minus 0.31 divided by the square root of, and we're using p sub naught for this, keep that in mind. So it's going to be 0.31 times 0.69 divided by 8,368. I'll calculate the standard error separately. I know it's going to be 0.01 up at the top. And I got 0.0051. So an incredibly small standard error. Okay. If I go ahead and calculate the z-score on this, I get 1.978. All right, so now if I look at this, my true normal distribution should be look like this, basically. So right here in the middle, I got 0.31, I'm sorry. Right here, the first standard deviation, that's going to be 0.315. The second one is going to be about 0.32. Down here, the first standard deviation is going to be 0.305, and the second one is going to be 0.30. So we're looking at this value about right here. We want to see if this is statistically significant from our 0.32 up. Okay, let's do it. Normal CDF of 1.978 up to positive infinity with a standardized normal model. And that is 0.024. So this would be our p-value, but this is where at the very end we need to remember one thing. What do we need to do?
Double it.
Double it. Remember, we're not saying that it's changing, just increasing. We're just saying it could change in any direction. So really, if I go back to my diagram, I'm doing a two-tailed test. It could be either one of those areas, the area up above and the area down below. So I will double this to give me 0.048. All right, now we can conclude, and we'll say, because the p-value of 0.048 is less than the alpha level. Remember, alpha and significant level are interchangeable, of 0.05. We reject the null hypothesis. There is convincing evidence that the education level of mothers has changed. Okay. So there we go. We're done with that. The last question here is, do you think this difference is meaningful? What do you guys think? Okay, I'll kind of answer for you guys. We went from 31% to 32%. That's a statistically significant difference. But in the end, do you think it's really a difference that matters?
Not really, because there's so many, like the population is so huge that like in the end it's not, I don't know.
No, I agree with you. I don't think it's that big of a difference. Now it's not no difference, and that is a good thing. It's gone from 31 to 32%. That's a good change. And on a very large scale, talking about all the mothers, then that, the raw numbers would be pretty big, but percentage wise, it's really not that big of a difference. So this is one that's statistically significant, but not super meaningful. So anyways, I wanted to go back to slide real quick, this one right here, because we already found the answer to this, that it was definitely a big difference, right? It went from 5% to 12%. But the last question we didn't answer was, do environmental chemicals cause congenital abnormalities? We got a statistically significant result. Did we prove that the chemicals were causing it?
I think, well, the sample was just of children that had signs of abnormalities, but those abnormalities could have been from maybe other factors besides chemicals.
Okay, perfect. Yeah. So we are not proving anything about this. All we're saying is that we have statistically significant results that show that the percent of abnormalities has changed, has increased. And just like you're saying, we're not saying why that's the case. We're not proving how that's happened. We're just saying that, yes, it has changed. Okay, so that's an important distinction to make. I'll jump past this. We're going to look at just one more together, and then I had other examples set up, but we're not going to do them. If you need more help, you can stick around. We can look through some stuff. Okay, this is an analysis that's already been completed, but you can tell there's a lot of, well, you can't tell yet, but you'll read through and see there's a lot of errors. So take a second just to read through the prompt. So after you finish reading it, I want you to look at just this part right here when they state their hypotheses. Do you notice any errors in the hypotheses? And you can either speak up if you notice an error, or you can circle and change where you think the error should be changed.
Shouldn't it be p-value instead of p-hat?
Yeah, I think so. That's actually not the mistake here. I think it should be P instead of P hat. I'm not sure if that's really a distinction that's going to make a difference. And Zach, I saw you circled that. We are going to have an error over there, but we'll get to that one. So does anyone see a problem in the hypotheses? Okay, just to move it along, I'll tell you this. It says that we're concerned that this is not accurate. This 90% figure is not accurate. We're not saying it's increased or decreased from there. So really this should be doesn't equal. That's really what we're testing right here. So that's an error. Now on this line, we are checking our assumptions or checking the conditions. Was a mistake made here?
Yeah, they the 750, that's just the sample size, and to do the large counts condition, they need to multiply it by the proportion of success and the proportion of failure.
There you go. Perfect. So they didn't do their large counts correct. So that's a mistake. And here we'd want to do 750 times 0.9. So we'll use P sub naught for this. And anyways, you know what to do from there. So yeah, there's a mistake. The next line, I'll tell you. Okay, well, anyways, if anyone has any ideas for the next line, what do you think there is a mistake here, and what do you think it is?
They're supposed to calculate the standard error, right? But it's the same equation as. Actually, no, it's not. But
There's one. Well, the one change between the two is important. I will tell you the equation itself being set up, because we were doing it with, of course, p hat minus p sub naught up above. That's a test statistic. That's not the error. You can calculate the standard deviation separately. So it's a problem in the numbers they picked.
They used p hat instead of just using p.
There it is. This is p hat. And that's 1 minus p hat. So we do not use p hat for this. We use p sub naught. That should be 0.9 and 0.1. Because p hat, remember, is that value right there. Or sorry, p sub naught is that one. So there you go. There's a mistake. They calculated an incorrect standard deviation, standard error. We'll just move ahead. I'll go ahead and tell you, just so we're not racking our brains. This line, there's really nothing wrong. They're using the wrong number down here, but we already know that. So we'll just move ahead. What about in the next line? Any mistakes here?
They should have subtracted the 0.977 from 1.
Yes, that's kind of, you're basically right. Here's what they did. They had a -2 test statistic, and they measured this way. But we always measure the area of the tail. So that's another way of kind of saying what you were, is they should have measured, this should be z is less than -2. Which would have been the same as 1 minus that. So it would have been 0.023. Okay, and I'm not going to bother with the last part. They made, well, I'm not going to write anything. More than a 97% chance that the stated percentage is correct for this region. That's really not how to interpret a z-score or a p-value. We would say, we didn't ever explicitly say it. Well, oh wait, I'm jumping ahead. We're also supposed to multiply that by 2 to get 0.046 because this is a two-tailed test. All right. So forgot about that a little bit. So here's our p-value, 0.046. And now is where we could say, because our p-value is less than our significance level, which we'll assume is a 0.05, we can reject the null hypothesis that, and we have convincing evidence that this proportion has changed. Okay. So that's all fun stuff. Let's just wrap this up. We've got now your homework. Not much more to it. We're going to begin chapter 23. We're going to be looking at the same kind of thing, but with means tomorrow. So, and actually, no, we're going to be looking at something different. We're actually going to do means on Monday, but you can start reading chapter 23 right now. Technically, we're doing chapter 21 tomorrow. So if you want to read through that, I should have changed that. So chapter 21 is a good thing to skim through tonight, but chapter 23 also. All right, having made that correction, that's all there is for today. Hope you have a wonderful rest of your day. If you have any questions, you can stick around.